So welcome everyone to today's HEP-TN Seminar. We're very happy to have Erez Zohar from the Racah Institute of Physics and also the Quantum Information Science Center at the Hebrew University of Jerusalem. And today he'll be telling us about how to eliminate fermions using gauge fields. Erez, please, thanks a lot for giving the seminar. And please, it's all yours.
Thank you, Suki, for inviting me to give that talk. So indeed, I will tell you today about some method that we developed some time ago, which allows to map fermions to hardcore bosonic degrees of freedom, spins if you want, in the presence of gauge fields. And it's done in a way which is completely local and can be done in arbitrary space dimensions. So there are many details, and at some point I will get a bit technical, so I apologize in advance. Stop me if I'm going too fast. But it's really important for me to pay attention to some details to make sure that everything here is clear. Basically, this is not my latest work, but I'm very happy that I was asked to talk about it because it's actually something I'm always happy to talk about and show this trick that we are doing. So basically, what is the starting point? Let's go a bit back in history, something like 6 years backwards, and look at the situation back then of the field of tensor networks for lattice gauge theories. So today, I'm sure you're all familiar somehow with either tensor network studies for lattice gauge theories or quantum simulations thereof, and it's quite a big field with many people participating. But back then at the time, there were already quite amazing, remarkable numerical works in 1D that used the MPS and DMRG for lattice gauge theories. And people started looking at ways to extend these constructions to further space dimensions, which obviously in most cases involved the generalization of MPS to PEPs. And in many cases, these works were rather more analytical than numerical. So I want to remind some of these things. So basically, I guess the first one that should be mentioned was this work by Tagliacozzo and Vidal, which in which they considered a pure gauge tensor network construction for a pure gauge Z2 gauge theory. And later at ICFO with Alessio and Maciek, they introduced some other pure gauge construction, which allowed to consider both analytically and numerically tensor network states in two space dimensions for pure gauge theories, this time with continuous groups. Afterwards, there was this other work, which was mostly analytical, a collaboration between people at Ghent and people at MPQ, which was done in a slightly different perspective since it introduced this idea of gauging. And what's the idea of gauging? They basically suggested to consider some PEPs with a global symmetry, that is some state that could be thought of as something that describes matter with some global symmetry, and then to lift this symmetry to the level of a local one. Something, if you want, which is analogous to the minimal coupling procedure that is usually done for Hamiltonians or actions, this time on the level of the state, which was possible thanks to the very special way PEPs are constructed. And in this case, they considered the gauging procedure that they introduced involved the introduction of gauge field Hilbert spaces that were identical to those of the matter. which in some sense, I will elaborate on that later, corresponds to introducing, considering theories with Higgs-like matter. Later, we started with another approach that suggested to gauge PEPs with the global symmetry. Basically, the basic idea is similar. You take something which represents the matter and you lift the symmetry to be local, which requires you to introduce a gauge field. However, in our case, we considered gauge field Hilbert spaces that were different than the ones of the matter and looked a bit more like the ones used conventionally in lattice gauge theories. That allowed us in particular to propose some fermionic constructions to take what we called gauge Gaussian fermionic PEPs, where we constructed Gaussian PEPs, Gaussian fermionic PEPs, states that represent the state of some free matter. And with our gauging procedure, we added some gauge fields to it, some quantum gauge fields, some extra Hilbert spaces that allowed us to use these states as ansatz states for lattice gauge theories with fermionic content. And eventually, after playing with some toy models, we also found some method to connect it with Monte Carlo that doesn't see the sign problem and use it for some actual numerical computations. So there is some differences you see between these two gauging approaches, and it mostly has to do somehow with the different nature of the Hilbert spaces. In this former gauging procedure, the one that I called Higgs-like, they found some very nice feature, which is that one can eliminate, with the use of some local controlled operations, one can eliminate the matter field and remain with the PEPs that describes exactly the same physics, but only with gauge fields degrees of freedom that are no longer gauge invariant. And this, in some sense, is exactly equivalent to the transformation which is done normally in the Higgs mechanism after you perform the quasi-classical treatment and you get rid of the Goldstone modes. You do the so-called unitary gauge fixing and eliminate the matter, and actually this is the thing that allowed for that there. Then in our case, we used to think that one cannot eliminate the matter field. It looked pretty obvious in the beginning. And we were thinking, what we believed also, when we were discussing it with other people, is that this had to do with the fermionic nature of the matter. Because, you know, fermions are always special and demand some special treatment, and they come with their special statistics and non-locality. So probably something that has to do with that doesn't allow us to repeat this trick. But then what turned out that actually, and this is what I'm going to tell you about today, one can eliminate the matter in spite of the fermionic nature in a way that is pretty much analogous to what they did in the other gauging scheme, or what is done in the Higgs mechanism. So this is what I'm going to tell you about today. Basically, we started, when we just started with it, we thought that it was some artifact of this particular PEPs construction, but it turns out to be a much more general feature of some lattice gauge theories. I will define it better when we get into the details. So I'm going to show that to you completely disconnected from any particular PEPs construction. So basically, fermions sometimes tend to be intimidating for people. I see them elegant, and there are many, many possible words that people can use to describe fermions, depending on, I mean, I'm sure you all have your favorite approach, depending on how much you hate or like dealing with the Fock spaces. But all these special features, in some sense, have to do with the non-locality of the fermions, or the tail that they have. So what am I talking about? Fermions are non-local. In what sense? If you consider some bosonic theory, one of the basic things that define bosons is the different bosonic modes commute. This allows us to factorize the Fock space or the Hilbert space of bosonic systems as a product of the different Fock spaces of the different modes. When we consider fermions, however, this doesn't hold, because the basic fermionic algebra tells us that the fermionic modes, and in particular the creation operators, anti-commute. And anti-commuting means in particular that they don't commute. Sorry. And this can be seen as some non-locality that the fermionic Fock space involves, because two fermionic operators at two arbitrarily far coordinates do not commute. This doesn't allow us to factorize the fermionic Fock space in terms of the different fermionic modes, unless we specify some order. But this is a pure fermionic property. If you want to see what happens to fermions with bosonic or with first quantized objects that live in different spaces, they commute and behave very well. So it's really something that has to do with the fermions. Now, how can we explicitly see this tail? We can look at the Jordan-Wigner map that is used, I'm sure we all know it very well, used in order to map fermions to spins. So of course, if you want to represent a fermionic creation operator by a spin raising operator sigma plus, it will be good only if you have a single fermionic species in your world, because sigma plus and sigma minus anti-commute and it's great. But if you want to consider more species, the special anti-commuting of different modes must somehow manifest itself. And this is something that this transformation does, this mapping does, by introducing a tail. We must order the fermions, the fermionic modes in some way. If our system is one-dimensional, we have some natural choices of ordering, but of course, the order doesn't really matter. And once we order them, instead of representing the fermionic creation operator by a spin raising operator, we take this raising operator and multiply it by a very non-local tail, some long string that involves operators, in this choice sigma z operators of all the previous spins, all the previous fermions, and this allows us to obtain the anti-commutation. This is something which is explicitly non-local. Unlike the general fermionic anti-commutation relation, which doesn't involve any operators which are explicitly non-local, when you do that, you actually expose the tail. And when you map to spins, this non-local tail is explicitly seen. So one can't get rid of fermions without any trace, which could be a nice dream or something that we might have wanted to do. Instead, we want to see how we can do it in the simplest way. For example, here we have a highly non-local trace, but maybe we can try to do something that will leave some local leftover instead. And this will be the aim of the transformation that I'm going to show you today. So for the start, let me quickly go over the lattice Abelian Higgs model, which in some way inspires this work. This is something that on the lattice was studied by Fradkin and Schenker in this seminal paper that was published in PRD in 1979. Of course, in the continuum, it was done before. And the situation is like this. They study it in the conventional way used in lattice gauge theory, in the action formalism, where both the space and time are discretized. And the degrees of freedom are the following. On each vertex of the lattice, we introduce frozen Higgs fields, or Goldstone modes, if you want. That means that on each side or vertex, I have these fields phi of r, which are just exponentials of some angular fields, of some phases theta that take values between 0 and 2 pi. Then on the links of this lattice, I place fields that mathematically are completely the same. These U operators that also carry some direction label, mu. They're the exponentials of some other angular fields A that take values between 0 and 2 pi. And of course, you can use it. This plays the role of a compact vector potential on the lattice. And you can use it to build a field strength tensor F mu nu using lattice difference operators and derive at some compact discretized version of this continuum field theory, the action that we see below here. It has two terms. The second one with decay, the cosine of F on all the plaquettes of the lattice. This is something that becomes the pure gauge F mu nu part. And then we have some coupling of the matter and the gauge field. The first cosine term tells us that the gradient, the difference between the theta field, the matter fields on the two edges of a link, the two sides of a link, is coupled to the, the gauge field in the link in the middle. And this is gauge invariant. We have here this discrete version of gauge invariance when we take our A and shift it by the lattice gradient of some function alpha defined at the vertices. And we also take the phase that represents the matter and shift it by the same phase. And then the normal procedure that one does when the Higgs mechanism is studied is the unitary gauge fixing. We want to basically get rid of the matter degree of freedom. This is the step of the Higgs mechanism, which is always referred to as the gauge boson. The vector field eats the Goldstone modes, becomes massive, the Goldstone modes disappear, and the gauge symmetry is lost. So this is done by performing some gauge symmetry where the function, where the parameterizing function is theta, the matter field. If we do this transformation, which is here, what we obtain is a new action that we see below. Nothing happens to the pure gauge term because it's gauge invariant, it's pure gauge invariant. And the first term of the matter becomes what will become in a continuum limit mass term for the gauge field, the cosine of A. So we lost the matter degree of freedom, but we also broke the gauge symmetry. That's what is always done there. In order to connect it to what we want to do, the first thing I want to do is to reformulate it in the Hamiltonian formulation with in the Hilbert space picture. So let's begin with that. So in the Hamiltonian formulation of lattice gauge theories, the lattice is only in space. Time is taken as a continuous, and in our case, a real coordinate. But as in the action formalism, the matter fields will reside on the vertices, and the gauge fields will reside on the links. The theory we are talking about here is Scalar Lattice QED. The matter field that we have on the links is described with these capital phi operators, which these are complex fields that can be decomposed in the form of a radial real field times the exponential of some angular field. These R and theta are two independent fields. They commute with each other. And then if we add some Higgs potential, we can minimize it quasi-classically and fix the radius to some constant R0 that has to do with the minimum of the potential. Then we are really left only with a field that is the exponential of some angle phi, the case that we previously saw. We define a charge operator Q at every vertex, which is an integer spectrum, but it's not bounded, okay? Its eigenvalues can be any integers from -∞ to infinity. It's like the angular momentum of a particle on a ring, the angular momentum in planar rotations. It's canonically conjugate to this matter field or coordinate theta, And then what we have is that the exponentials of I theta are raising operators of the charge, which we can get from these canonical commutation relations. On the links, we introduce U1 gauge fields, which have exactly the same Hilbert space. That means that on each link, which emanates from some vertex x in a direction I, we introduce another another compact variable phi, and we have some unitary operator, which is the exponential of it. As on the vertices, the phi is canonically conjugate to some quantity which take a non-bounded integer spectrum. Phi plays the role of the vector potential. In the previous action formalism, it was called A. So the conjugate momentum is the electric field E. And since E and phi are canonically conjugate, the operator e to the I phi or U simply raises the electric field or the electric flux on the link by 1 unit. Out of this, we can construct the Hamiltonian of scalar QED, which involves the following terms. First, we can consider the terms that include only the gauge field, the pure gauge terms, which is we call it the U1 case of the Kogut-Susskind Hamiltonian, which is the pure lattice gauge Hamiltonian. And we have some terms on the link, the blue terms, E square, which are just some kinetic terms that in the continuum just give us the electric energy. And we have the interaction of the phi's around unit squares, around plaquettes, this cosine term, which in the continuum, if we becomes the magnetic energy, since basically we have the cosine of the lattice curl of phi, and in a careful continuum limit, it becomes curl A square, which is B square. But this is not important for this talk. The other type of terms that we have is the interaction between the gauge field and the matter, which takes place on a link, this H int that we have here. Basically, what it tells us is that when a charge moves between two neighboring vertices, let's say hops from the vertex x plus unit vector in direction I to the vertex x, something must also happen to the gauge field in the middle, in a way that will keep the symmetry intact. And in particular, in our Higgs case, when we fix the radial field, the interaction Hamiltonian has this cosine form, phi on the link of the gauge field minus the difference or the gradient of the matter phases on the edges. So this is very similar, no surprise, to the action terms that we saw before. We have some local symmetry here. This thing is gauge invariant, which means that we have generators at each point of space. This is something that we have when we have a local symmetry. What are these things? We define on each vertex the operator G, which is the divergence, the lattice version, the discrete version of a divergence of electric fields around this vertex. So you see in this 2D example, we have this figure here that shows us that we take the electric fields on the outgoing links with some positive signs, and we subtract the ones on the ingoing links with a negative sign. The fact that we have the local symmetry tells us that we have some constraints that are satisfied at each vertex, at each x of the lattice, which we call Gauss laws. The divergence of the electric fields acting on a physical state is equal to the charge, the matter charge on this vertex acting on the same physical state. That means that G minus Q is a constant of motion. And this is indeed the generator of the symmetry. We have such a generator, G minus Q, which commute with the Hamiltonian at each lattice point X. Now we want to discuss this unitary gauge in this formulation. What we want to do is to find some unitary operator, like we always do when we implement transformations in quantum mechanics, some operator U, that when we act with it on the vector potential phi, will give us this addition which depends on the matter fields on the two sides of the link. Why? Because if we have this transformation and we transform this interaction Hamiltonian with that, the matter fields indeed disappear, which is what we want to do with this unitary gauge fixing. How do we do that? We basically want to shift phi. We want to translate phi. In order to translate phi, we need to generate a transformation that translates phi has to be generated with its conjugate momentum. And the conjugate momentum of phi, we said, is the electric field E. Therefore, the transformation will look like that. We take a product of all the links, and we want to shift each phi by this difference, theta at one end minus theta at the other, and multiply by the generator E. Very simple, and all these operators that we have in this term commute. Since they all commute, I can change it from something which involves action on the links to something that involves action on the vertices. I can group things in terms of theta. Look at theta as the generator, as some transformation that transforms the matter field instead. So I can write the same thing as a product of local transformations on the vertices generated by theta, and each theta is multiplied by this divergence of electric fields at the point, which we saw when we defined the Gauss law. Then we have a product of local operators that act on each lattice site, on each vertex. So as I said, we recognize it as some controlled operation in which we act on the matter with theta, and it's controlled by the divergence of the electric fields. It means that I change the charge. We said that e to the I theta is a raising or lowering operator of the charge on the vertex. We change the charge at the vertex with respect to the divergence of the electric field around it. However, we have Gauss law. Gauss law guarantees us that the divergence of the electric field G equals the charge that we have at the vertex. So what this transformation does is to locally get rid of the charge that I have on the vertex. I just write down this operation, which is controlled by the gauge field, by the operator G. And I'm exploiting the fact that the Gauss law, the local symmetry, tells me that the divergence equals the charge. Then this is really what we do in this unitary gauge fixing. If we look at it in this Hilbert space, in this Hamiltonian picture, it simply eliminates the matter field, reduces the charge at each point to 0. Yeah, so this is a controlled elimination of the matter, as we said. We begin with an initial state that satisfies the Gauss law, that is gauge invariant, G equals Q, acting on physical states. I can expand any such state as in some basis with product states of some gauge field configuration and some matter configuration, and the amplitudes will have this constraint that Gauss law must be satisfied. And then whenever I act on one of these constituents, thanks to this constraint that I have here, each part of this superposition, we will exactly reduce the amount of charge that is given by the divergence of the electric fields. So the result of acting with this U will give us a state that contains the same gauge field configurations with the same amplitudes in the superposition, and therefore will store the same physical information. But the matter field completely decouples. And there is no Gauss law anymore, which is a manifestation to the fact that the gauge symmetry doesn't exist any longer. It's broken. So what all has to do with the Gauss law. which we know from the continuum in this form of divergence E equals rho, and here we have this lattice quantum version, which relates G and Q. While this is a differential equation for the electric field or difference equation on the lattice, it is an explicitly solved algebraic equation for the matter. So you see, the matter, if I want to solve it for the electric field, I will have to invert this divergence somehow, which I can do non-locally in 1D, but it's a problem in more dimensions. On the other end, we have explicitly a solution for the charge in terms of the electric field. We don't need to do anything to this equation if this is what we're looking for. This can be solved in any dimension. And as we saw now, we can exploit it in order to eliminate the matter with such local controlled unitaries. Obviously, it works in this Higgs case. But does it work in other cases, and in particular in the fermionic case? This is what we're going to see now. Any questions before I move on? Okay. Right, so the question is whether we can do it with fermions. I want to do it with fermionic matter. So first of all, we need to formulate a bit. Now I'm in a different situation in which the matter is fermionic. I choose the staggered fermion formulation, which was introduced by Susskind in the 70s, which means that at each vertex of my lattice, instead of placing the scalar field phi, I place a single fermionic mode created by the operator psi dagger, annihilated by the operator psi. The essence of this staggered construction is that the even sublattice is for particles, and the other one for antiparticles, because instead of having two components of the spinor at one vertex, they are distributed over two or over more if we work in more dimensions. This is a way to avoid the so-called fermionic doubling problem, which we're not going to enter now. So having these definitions of the charges, I can redefine the operators G such that on the even sides, there will be the divergences, and on the odd sides, there will be the divergences of the electric fields plus one. And when I have that, the Gauss law will have this simple form that G acting on the physical state at each place is equal to the number, to the fermionic number operator acting on this side. No matter if it's, it doesn't depend on the sublattice. G equals N acting on physical states. And I want to use this somehow in order to eliminate the matter. So in order to do that, let us first try to construct an analogy with the scalar case and see if we get stuck. So in the bosonic case, in the Higgs case, we said before taking this quasi-classical choice of the radial field, we had this creation operator phi dagger, which was the product of some radial field R and some angular field theta. Let's try to do the same with the fermions. Let's write some radial field eta and some phase C, and we have to define what they are. We're going to do that. In the bosonic case, e to the I theta was the U1 phase. So here, let's try to choose C to be a Z2 phase operator, some fermionic operator that squares to the identity. Why Z2? Because Z2 has to do with the fermionic parity symmetry, which we're going to discuss a lot today. So if C is a fermionic operator that squares to 1, we should try to choose it as a Majorana mode. It's an operator that squares to 1, and the different Majorana modes on different positions anti-commute. Okay, let's move on with the analogy. So this agrees with what we had, the different thetas on different vertices commute, just trying to say, bosonic case, we have commutators, and in the fermionic one, anti-commutators. Then in the bosonic case, these two components, r and theta, commute. So let's try to choose some eta that will anti-commute with this C. This in particular tells us that the C inverts the sign of this eta, whatever it is. Now, demanding that all the fermionic algebra will be satisfied, the different anti-commutation relations of psi and psi daggers, given the anti-commutation that we want for the Majorana modes and between C and eta, what we get is that eta, the eta operators on different vertices commute, but on the same vertex have to be anti-commuting. So it means that this eta is something that behaves, that is bosonic on different sites, but fermionic when the same site is considered. Okay, so let's try to find, if we continue this analogy to the scalar case, find a local unitary that takes the U on the link and multiplies it with these C operators on both ends of the links. Where is the analogy? In the scalar case, we took the operator U and multiplied it by the phases e to the I theta on both sides. Here the phases are C. Let's try to do it. If we can do it, if there is some unitary U that does it and commutes with the original fermion psi, what we obtain eventually is that psi dagger U psi, what we have in the interaction term, becomes now psi dagger C U C psi. And then we can unite psi dagger and C on one side and C and psi on the other side, using our definition with the C and the eta, to these eta operators, which are bosonic off-site. So this should help us get rid of all the non-locality, because etas on different vertices commute. However, can we do it? No, we can't. And the easiest, the most trivial answer is that fermions can't be simply replaced by hardcore bosons or spins, because basically what this would imply is that I can take each psi dagger operator and replace it with a sigma plus. This operator satisfies these eta relations. And we know we can't do that just from our experience, that fermions have, that when we use spins, they don't have fermionic statistics. We need a Jordan-Wigner transformation to fix that. Another reason is that it can't be unitary, because if we check carefully, the U operators on different links commute. But when we act with this transformation, they don't commute anymore when I consider CUC on intersecting links, because of the fermionic anti-commutation of the Cs. So if a transformation that doesn't preserve commutation relations can't be unitary. So this doesn't work. However, let's try to push this analogy a bit further, although we know it doesn't work, in order to see what exactly we have to do and what we have to fix. So in the scalar case, we had the local transformations that had the form of e to the I theta g, or if you want, the e to the I theta, the operator that changes the charge of the matter on the vertex, to the power of g, the divergence of the electric field. If I want to write it in terms of the fermions, just to perform a naive replacement, it will look like this: the fermionic phase, which is the Majorana operator, to the power of g. Now g can take only the values 0 or 1 in our physical Hilbert space, because we have the Gauss laws that relate g to fermionic number operators. If g equals 1, it means from the Gauss law that there was some fermion there, so C acts and gets rid of it. If g equals 0, it means that there is no fermion to annihilate, and therefore no action is taken. So it looks fine. What is then the problem? I can take this C to the power of G and decompose it to C to the power of all the constituents of this G, the different electric fields in all the links that go around my vertex. And if I do it carefully, I will see that indeed this transformation multiplies the operator U by C from the left and by the other C from the right, and everything looks good. So what's the problem? The problem is like that. I define the local transformation to be C to the power of G. And then I say that the transformation that acts on the whole thing is the product of these local transformations. And here comes the problem, this product. Since these local transformations C to the power of G don't have a well-defined fermionic parity. C is an operator which has odd parity. And if G is 0, U is the identity and the parity is even. If G is 1, U equals C and the parity is odd. Therefore, U of X doesn't have a well-defined parity. And I can't say that the different U's in different vertices, therefore, they don't have any particular commutation or anti-commutation relation. It means that this product that I have in red here is ill-defined. I can't write down a product of these U operators without specifying in which order I'm doing that. So I must specify some ordering. And once I specify this order, and then when I do that, what I find out is that in the Hamiltonian that I transform like this, I will start seeing some very non-local strings that will involve some sign factors that look like -1 to the power of the electric field along the strings, which depend on the ordering I choose. So I get what I want, but I get these extra non-local tails, which is something I definitely don't want. And therefore, this road is bound to fail. So it's a unitary transformation, but it's very non-local. How can we fix it? Let's try to analyze this situation. Fermions in physical theories, if we exclude supersymmetry, are always subject to a global Z2 symmetry, which is associated with what we call fermionic parity superselection. That means that the superselection rule that we know very well tells us that we shouldn't consider superpositions of states with an even number of fermions and an odd number of fermions in the whole system. This transformation that we just finished deriving violates the parity locally. The UX, the local ingredient, which doesn't have a fixed parity, violates the parity in a local way. Sure, the product of all the U operators conserves the parity globally, but since the local ingredients violate it, we must specify some ordering that gives rise to non-locality. So what we should try to think about is how we can preserve the parity locally. And this is done by introducing some auxiliary fermions. So in order to do that, I want to introduce more fermionic species that will, in an almost miraculous way, they will disappear from our final result, I promise. And I'm going to introduce two types of those. One type I define on the vertices, operators that I call C. And they will be, so what we did until now, we should consider as a sketch, as some idea that failed. And now let's start formulating something from scratch. At each vertex, I define Majorana mode C, which is related to a regular fermion chi. Okay, it's the Majorana fermion, which is the sum of the annihilation and the creation operators of the mode chi. This will help us to keep the statistics, and we will see how. The other type of auxiliary fermions, I call them parity keepers, and I place them on the links. I put on each link two auxiliary Majorana modes, alpha and beta. The alpha modes are associated with the beginning of the link, and the beta modes are associated with the end of the links. And the alpha and beta modes of one link are related to the same normal fermionic mode, which we denote by F. So far, only definitions. Now what I want to do is to fix the transformation that I had. The transformation that gave us what we wanted, I remind you, was C to the power of the divergence of the electric fields on the vertex, on the links around the vertex. However, we had the problem with the parity. Since C squares to the identity, it doesn't matter if I take in the exponential the divergence of the E's or the sum of the E's. Sorry. So then my transformation can be C to the power of one electric field in one direction, C to the power of the next, and the next. All the four if I'm in 2 dimensions. What I'm doing now is to each such C, I attach I times the Majorana operator that has to do with the leg on which, with the link on which this electric field is defined. So instead of a product of 4 operators are the same C to the power of some electric field, I have IC times an auxiliary Majorana to the power of E. Each of these ingredients, IC alpha, IC beta, each of them is unitary, and each of them has even fermionic parity, because we have 2 fermionic operators there inside. It doesn't matter if E is even or odd, it has even parity. Therefore, this mu U that I constructed here doesn't violate the local fermionic parity. Different U's on different vertices commute. They are on each vertex, my U on each vertex is even fermionic parity, and it includes only fermionic modes that are associated with that vertex. The U's of different vertices contain different fermionic modes. They are even operators, they commute. Therefore, I can write my global transformation as a product of all the local transformations without specifying the order, because they all conserve the parity locally. On the other end, these local U's are still proportional to C to the power of G, which is what we wanted. Another nice feature of this transformation is that it commutes with the physical fermions psi. These are just some other fermions, and U is even, so they commute. So now I have to see what happens when I act with these operators on the link operators UIX. So I don't want to bore you with the details, but it works like this. Each U is composed of 4 parts. So suppose I'm considering the transformation of a horizontal link. The first one I act with has to do with the link I act on. So this E doesn't commute with the operator U. I act with this part of the transformation. And what I get at the end is not only C times U, if I do this arithmetics carefully, I also have this alpha. The parity is the same. I had U, which had no fermionic operators. Now I have C alpha U, which has 2 fermionic operators. It's still even. Then I move on with the other pieces of the transformation, which simply decorate this term. They put this -1 to the power of the electric fields on some of the links around the vertex. So I changed it a bit, but it's still local. I can move on and perform the same trick on the other side of the link. And what I get at the end is that my U that I had in my interaction now has C from the left, C from the right, which I wanted, and also the alpha beta on this link. And then I have some phases -1 to the power of the electric fields of some of the links around this link. Something changed. The interaction now involves more links, but it's still local. And all these things I absorb in some sign factor that I call Xi1. I can do the same for the vertical links, and I will get a different form of phase factor that will have to do with other links around the link I'm interested in. Now, what happens when I want to use it in my Hamiltonian? So I begin with my psi dagger U psi. I perform this transformation. I have this sign factor that commutes with everything, and I'm not going to consider it at the moment. Then I have this psi dagger C and C psi, which I can absorb to some eta operator, like the one we wanted to have in the beginning, something which is fermionic on-site, but bosonic off-site, which is almost what we want. but we still have to somehow get rid of these new fermions that we have here, alpha and beta. And this is a very interesting trick. And for that, we have to specify actually what is the Hilbert space that we act on. Because we have our physical state very well defined. We start with some state psi, which is gauge invariant, therefore satisfies the Gauss law, G equals N. And initially we begin with this physical Hilbert space that contains all the states that satisfies them. Our original Hamiltonian acts within this subspace, within H phys, because it is gauge invariant. But we can choose what we want to do with, for the initial condition before the transformation of the auxiliary fermions. So what we're going to do is to say that the auxiliary fermions start in their Fock vacuum. That means that the ones on the vertices are in the state omega 1, which is annihilated by all the fermionic annihilation operators on the vertex chi of the auxiliary fermions, and also on the links. We just don't have them to begin with when we start with the transformation, before we start with the transformation. And so we choose an initial state, which is the following. We embed the original gauge invariant state in this space, which has the same dimension, the original one times the Fock states of the auxiliary spaces. So the Hamiltonian is trivially changed to the original one times the identity operators of both auxiliary spaces. The Gauss law is still satisfied. Now we want to see what happens to the transformed states. What are the properties of the transformed state in which I take this initial state that I picked and act on it with the operator, with the unitary U. One very nice feature of this transformation is that it completely commutes with the product of the alpha beta auxiliary modes on the link. To begin with, I start on the link with an auxiliary vacuum. That means that the product of alpha and beta, once I represent it in terms of normal fermionic operators, is identical to minus I in this in the physical Hilbert space I work on. Once I choose this initial condition, this empty Fock space initial condition for the auxiliary fermions. However, since these products of alpha and beta are unchanged by the transformation, when I finish the transformation and I have a product of alpha beta, I can just safely, since I'm only operating within a particular subspace of my Hilbert space, replace them by minus I and get rid of them. And I remind you that in the transformed interaction that we had, we actually add alpha beta only in this product. So I can just get rid of them at once, forget they ever existed, and replace them by minus I. They are merely here in order to preserve the parity symmetry locally. Okay, we got rid of those. Now we still have, so our Hamiltonian looks like that. And what happens with the first type of auxiliary fermions? Naively, we can say, why should we care? They don't appear in the Hamiltonian. But we also have some set of constraints. The original Gauss laws remain. They are left untouched by the transformation, and we can rephrase them in terms of the hardcore bosons. But we also have another Gauss law that tells us that the parity of the auxiliary fermions chi on the vertex is the same as the parity of the charge on the vertex. It looks a bit trivial when we consider U1 and the charge is 0 or 1. But when we go to non-Abelian theories and the charges, and we can have different particle numbers on each vertex, we still get such an equation in which we just need one chi to measure the parity of all the modes that we have on the vertex. So this means that these auxiliary fermions on the vertex just count the parity. Then when we can, in a sort of superficial way, if we look at this expansion of psi dagger equals eta dagger C, we can think of eta dagger as the thing that covers the physics. These are hardcore bosons. They are the ones coupled to the gauge fields. They appear in the physical conservation laws, the Gauss laws. And all the charges, the bilinear operators, are constructed out of them. The C's factor out. The C operators only count the statistics. They only have to do with the statistics. They count the parity of the physical ingredient eta. So if we can actually get rid of the C's, if we perform a local Jordan-Wigner transformation on each vertex, not a non-local one that will involve all the fermions, all the spins around the lattice, but a local one, which maps the two modes, the two anti-commuting modes that I have on my vertex, psi dagger and C, and I can map them to two spins that satisfy some constraint, which tells me that they have the same parity. So I can just do this Jordan-Wigner and then act with a unitary that will leave me using this parity constraint only with one spin, which means that effectively, in our case, I can just replace all the fermions in my theory by spin lowering and raising operators, but I need to add on each link this sign factor that depends on the sign of the electric fields, on the parity, sorry, of the electric fields of some of the surrounding links. And this is the thing that absorbs the fermionic statistics, okay? I can't just replace the fermionic operators by spin operators. I need to add this sign factor, which now takes charge of the statistics instead. So in my final Hamiltonian, I will just have these decorations, these sign factors that depend on some links, either on these link interactions or something similar in the plaquette interactions that will not calculate now. But the important thing is that all the terms remain local. No non-locality was introduced here. We only introduced these sign factors that depend on the electric fields on some nearest neighboring links, and they absorb the statistics. What did we gain? So as I said, the gauge field absorbed the statistics. The matter is now represented by hardcore bosons. We don't need to use fermionic Fock spaces, and we can just use factorize things to tensor product spaces. The fermionic statistics is taken care of now by strings of electric parity operators. All the terms in the Hamiltonian remain local, although the range of interaction is slightly modified to the neighboring links. Why was that possible? Because as we said, the fermions are subject to the global Z2 symmetry of the parity. And here we consider the U1 gauge theory. Z2 is a normal subgroup of U1, okay? And therefore, the local symmetry that we have of U1 includes a local Z2 conservation law, which states that the fermionic parity on the vertices is the source of the electric fields of this Z2 subgroup. These local constraints allow us to write down local and control transformations, as we did, that will transfer the statistics to the gauge field. We only used a finite subgroup of the gauge group, unlike what was done in the Higgs case, and therefore we didn't break the symmetry. We only changed the way that the statistics, which is related to the particular subgroup we use, Z2, is handled by the theory. And therefore, even when the theory is formulated with hardcore bosons, with spins, we still have some leftover, we still have the Gauss laws. The gauge symmetry is left intact. Also, it's important, before I speak for 2 minutes about generalizations, to pay attention to the fact that the analogy to the Higgs mechanism is with respect to the unitary gauge fixing, right? We are not talking about absurd things like condensation of fermionic fields here. I'm just talking about the mathematics of absorbing the matter fields by the gauge field, which in some sense is a side effect of the conventional treatment of the Higgs mechanism. Now, what can we do in other dimensions? Basically, it's very straightforward to generalize it to other space dimensions, one dimension, of course, and also higher dimensions, because we just need to repeat the same construction, add more auxiliary fermions, and that's it. What about other gauge groups? So a similar procedure, the procedure can basically be copied for every lattice gauge theory where the gauge group contains Z2 as a normal subgroup, we exploit only this part of the symmetry, which can be Z2n, SU2n, UN, which includes U1. In the case of other gauge groups, what we can do is introduce an auxiliary Z2 field without any dynamics in the Hamiltonian and use it in order to perform this trick. So yes, we introduce another degree of freedom, but this degree of freedom comes with very small Hilbert spaces and allows us to get rid of the Fock space description and forget about non-local tails, so it might still be useful in some sense. Similarly, it can be applicable to fermionic theories that doesn't, on the lattice that don't have any gauge field at all. Because what we can do is just to gauge them with some Z2 gauge field that takes care of the parity. It's actually a straightforward, there's a straightforward procedure for doing that. We can do it whenever we have a global Z2 symmetry, and we have it with symmetry, with the parity for fermionic, for physical fermionic theories. So then we can just do that and repeat the trick, even if we didn't have fermions to begin with. And if we have more complicated groups where the spinors have more indices, let's say color indices, the nice thing is that the same number of auxiliary fermions are used. We don't need to introduce more auxiliary fermions, even though we have more physical fermions. And the way it looks is like this. Our operators eta, dagger are now the components of the psi's times the same C. Because as I told you, C actually counts the parity on the vertex. Doesn't matter what is the exact particle content on the vertex. This is taken care of by the eta. But the C just tells you if you have an odd number or an even number and allows you to do that. And then we have this eta, which are not really spin operators. They are, as we said, something which is bosonic off-site and fermionic on-site, which means that in such a case, we will need to perform local Jordan-Wigner transformations on the site in order to represent the etas by spin operators, but they will involve no tails. Everything is done on the site. Now we can do a similar procedure. We can move one step further to completely eliminate the matter, which is either fermionic or hardcore bosonic, doesn't matter, if the gauge group includes enough U1 normal subgroups that will count the particles rather than the parity. Then we can write similar controlled operations that get rid of the matter field. And this is very similar to how the matter field is eliminated in the Higgs case. However, in the Higgs case, we had an infinite ladder of charges on site, and therefore we didn't have any constraint on the divergence of the electric field. Here, the divergence of the electric fields always equals 0, 1. So after we do that, we will need to introduce some projectors, some local projectors that will make sure that this is not spoiled, but that still remains local and is not a problem. So in some cases, it might be useful to completely break the gauge symmetry and eliminate the matter. And once again, it's possible if we have enough U1 subgroups. Otherwise, we can introduce an auxiliary one and perform the same trick. So to conclude, what I hopefully showed you today is that the fermionic statistics can be transferred to gauge fields that are coupled to the fermions, either if they existed there to begin with Z2 normal subgroup, or even if they didn't have this subgroup, or even if they didn't exist at all, we can just add it artificially and perform the trick. And this trick is unitary, it's local, it gives rise to no non-locality eventually in the Hamiltonian, and it can be done in any space dimension. And this pretty much summarizes the highlights of this transformation that I showed you today. And with that, I think I conclude. So thank you very much for coming and for your attention.
Yeah, thanks, Erez. Thanks for this clear presentation. So before we proceed to questions, let's all unmute and thank Erez. Are there any questions?
I do have a small question. So when you eliminate the matter, you're using somehow the Gauss law without any external charge. So does this mean that you have an effective description of like no static, so static charges, I mean. So you would have static charges. What does change? So does the Hamiltonian retain some non-locality, or you would do something different?
No, it doesn't. You just have to shift to redefine this divergence operator, because basically you don't, the different sectors of the static charges are not mixed. Here I focused on the case without static charges, but if you want to perform this trick with some static charge configuration, you just have to change a bit some things for this sector. So you will have to redefine this G operator. Instead of being the divergence of the electric field, it will be the divergence of the electric field minus the static charge. And then you will get the same result. So yes, it has to be written in a different way for each charge sector, but luckily they are not mixed by the Hamiltonian, and in any case we focus on one, so it works.
Thank you.
So Erez, I have a general question. Could you say something about advantages of doing this mapping in the context of numerical simulations? So let's say I have a fermionic PEPS and I can do this mapping and make it into a PEPS for a hardcore bosonic system to simulate the simulating the same system. So what are the numerical advantages of this map?
So the numerical advantages can appear if you really want to represent your fermionic operators by some local matrices. And this allows you to do that. Of course, it is not necessarily the most economical way to construct PEPs. In particular, we work on these constructions of fermionic PEPs. We take Gaussian fermionic PEPs and we gauge them. And then when we do the numerics, we use the Gaussian formalism, which is very simple and very efficient. So we actually don't need to use this trick. Right. So I can't tell you for sure that it's going to be more efficient for arbitrary tensor network construction. Where I can tell you that it can be helpful, on the other hand, it's something that emerged from the construction of tensor networks, but I'm not sure how much in general it can be helped, it can be used for simplifying tensor network construction. Where it can be useful is in a completely different context of quantum simulation. When we do quantum simulations of lattice gauge theories, usually we want to consider theories that are rooted in particle physics, in things which are part of the standard model or simple theory or similar theories. And there the matter is fermionic. The problem when you build a quantum simulator is that many simulating platforms don't allow you to use fermionic degrees of freedom. And traditionally, it has been thought that when you build a quantum simulator of a lattice gauge theory in more than one space dimension, and you want to include fermionic matter, you can only do it with ultra cold atoms, which do allow you to play with both fermionic and bosonic atoms and do all these things. But then there are other simulating platforms that can be more controllable or with longer coherent times, etc. And then they don't allow you to use fermions. So far until we came up with this, it was thought that they could only be used above one space dimension for the simulation of pure gauge theories and couldn't be used for simulating matter. Now with this, it actually gives rise to some new hope that one can extend the set of available platforms for the quantum simulation of lattice gate theories to other systems beyond ultra-cold atoms by using this trick. So this is where I believe that this is going to be very useful. In numerics, sure, if you do some some exact calculation for a small system and you want to avoid the tails, it can be simpler for you. But for the construction of tensor networks, the example that I can give you from my own work, when I work with fermionic PEPs, we don't need that. We work much better with the original fermionic terms. Perhaps one can write down some PEPs where it will be more useful. It's not something that automatically comes to my mind. It's something that emerged from the tensor network construction, and I think that the application is more in the quantum simulation world.
Okay, excellent. Thanks.
Thank you.
Are there any more questions? Okay, if not, let's thank Erez again.